Good morning, students. Welcome to the today's class. Okay, we have been discussing about designing with FPGAs and CPLDs. So this is actually the last class we have seen lecture number 3. Okay, so now we are going to look at the lecture number 4 on this one. So all these things that we have seen, and we stopped at what are the interconnections are there. Okay, so this is actually the lecture number 4. Okay, okay. So we have seen that an FPGA is actually the consisting of different CLBs, right? An FPGA chip is actually, it is an IC. So consisting of different type of CLBs are available. We have already studied extensively about the CLBs, how one CLB is connected to another CLB. So from this one to this one, or maybe this one to this one. Okay, how the connection is established between the CLBs. So that is what we normally call it as interconnections. Okay, that is we can call it as interconnections. There are the three possible ways that we can provide the interconnection between the components. Okay, between the CLBs. One is called a general purpose interconnect, what we can call it as general purpose interconnect. So where we have to use the switch matrix is the one of the important component. That means the switch matrix that we have to use. So for each and every component, we are going to introduce a switch matrix, something like this in between that one. So accordingly, it will be connected through the switch matrices. Okay, so as we can see here is the one logic block is there, second logic block, third logic block, fourth logic block, fifth and sixth, something like this. So therefore, in between those four blocks, we are going to use one switch matrix, right? So through this one only, the components will be connected. For example, um, so this logic block 1 is connected to logic block 2, for example. So therefore, through this link, it will be connected to this one. Okay, so like this. So if any block is connected to another one, certainly we should use the switch matrix only. So how the switch matrix is look like, something like this. Therefore, it has to consider, it has the switch matrix provide the connections for all the directions from this direction. So therefore, from the left hand side through the right hand side. Okay, and some this side and this side. So something like this, it will provide in all the directions. There is a possibility of the interconnections. Okay, so therefore, through these lines, for example, here we have one CLB is available, for example. So that here is another CLB. So the CLB wants to communicate it through this one. In any direction it will go. Okay, what is the simplest way that it can reach to that point? That will choose that part. Clear? So therefore, the intermediate point is we have to consider in this way. Okay, that is what the terminology that we have to use it here. So how it is connected from one, so whether the first path it can go, or this one it will go something somewhere else. That is depending upon the routing algorithm that we'll use here. Okay, so one of the important thing is that the switch matrix approach of interconnection is very expensive actually. Why it is so? The reason is that it has to connect all the possible wires. Okay, so that means that whatever the possibility is there, those many possibilities that we have to connect it in all the directions. Okay, so therefore it is actually establishing the switch network switch matrix is very complex actually. So it involves the very expensive in terms of the cost as well, because we have to provide everything. Okay, sometimes because of this the huge interconnects. Okay, that means that almost all the blocks are connected with the switch matrix. Means each and every every line will be associated with the switch matrix. Okay, so because of that one, it takes a lot of time. Even if it wants to communicate very adjacent to this one, it has to go to the first switch matrix and then come back to the logic number 2. So when the two adjacent, or whenever we have adjacent logic blocks are there, even for that one also, it has to go through the switch matrix only. Therefore, here we can say that the switch matrix is expensive in terms of the area, as well as the delay also will very high. Okay, so therefore the delay is also will be very high. So for example, as I mentioned that, for example, if you want to communicate from here to here, it's very less delay will be there. A small wire is sufficient. Otherwise, if you go to this one and the switch matrix and come to this point and will connect to this one, it takes a long path actually. Okay, so that is what the problem. But initially people will realize the switch matrix something like this only. And So this gain a popularity, but you have to keep in your mind these are expensive in terms of the area and delay, propagation delay. So that's the reason why sometimes it is called as we are not able to, then FPCA, the delay is not predictable. Unpredictable delay can be observed in case of FPCS. So whereas in CPLDs we will see in the later point of time, in the CPLDs the interconnections are very small, very smaller interconnections are there, and the delay is also predictable delay. Okay, the reason is only thing is that very small when compared to this FPGA, CPLDs are very less in size. Okay, therefore interconnects are very easy and we can predict the delay. But whereas FPGA is a huge IC, so the more number of components will be there. Very high resources will be there in FPGA. That's the reason why sometimes it is not possible to predict the delay as you expected. Okay, so therefore we have to go for the different optimization algorithms to reduce the delay of the circuit, right? So another approach to provide the interconnection is direct interconnects. Direct interconnects. So there is a small modification is there. For example, whenever we have an adjacent logic blocks are there. For example, this is adjacent to this one. Okay, so this is actually adjacent to this one. These two are adjacent blocks, logical blocks. So whenever it is possible, the adjacent blocks are there, direct connections can be possible. So that is how they have modified the interconnections. Okay, apart from this switch matrix that is available, they are going to introduce another technique is called direct interconnects. So therefore, adjacent block diagrams are connected, and the adjacent blocks are connected by directly. Okay, so therefore, by using this one, the fast communication or fast interconnections can be possible. Okay, for example, if you consider this one particular block, so it is possible to connect the four adjacent interconnects. So from this is the one, this is the second, this is the third, and fourth. So one particular logic block can communicate to other four possible or neighboring logic cells by using this direct interconnect. Sometimes from special cases, we can consider that diagonally also. For example, this is what, for example, this wants to connect it here. So therefore, through this block also, it is possible to connect it to this one. Okay, this is a special interconnect in the direct methodology. In the direct methodology, diagonal blocks are also able to communicate in a better fashion. Okay, but essentially, you have to understand that one particular logic block CLB can communicate at least four neighboring CLBs. Okay, at least four neighboring CLBs. So depending upon the FPGA, they're also possible to communicate in the diagonal also. So diagonal FPGAs also can be possible to communicate. Okay, so therefore, so in the special case, these are available. So therefore, out of one CLB can communicate eight adjacent CLBs. But you have to remember that minimum of 4 CLBs are mandatory in this particular direct interconnects. Clear? So because of that one, a smaller delay can be possible or observed in this particular direct interconnects. Clear? Fine. Now another one is that they have gone for another approach is called global lines they can use. Okay, so therefore whenever we have a high fan out, okay, whenever we have a high fan out and low skew clock distribution, okay, the delay you want to reduce is, and then more number of components need to be connected. Okay, fan out is nothing but one output will be connected to how many number of other devices. Therefore fan out is something else. We have one device here, so from device output will be connected to n number of components. Okay, n number of devices, for example. Therefore this is called fan out. Okay, so whenever we have a large fan out, then it is the best to uh, go for the global line approach. Okay, so in the global line approach, there are the two approaches are there. One is horizontal global lines can be available. Therefore this is one horizontal global line. Sometimes we can use also vertical global lines also. Okay, anything can be possible. These are all actually a tri-state buffers. Okay, these are all our tri-state buffers. Okay, therefore this is one of the another interconnect that normally used in FPGAs. Okay, so therefore if you go for one interconnect to another interconnect, main idea is that we have to reduce the delay of the delay when we are connecting one particular logic block to another particular logic block. So in that sense, depending upon your application or depending upon your what kind of FPGA that you are using, they will already they will intimate you that what kind of interconnects they have used, whether global interconnects they have used, or maybe the direct interconnect they have used, or switch matrix based interconnects they will use, or sometimes they will use in all these three interconnects depending upon the resource that they have available in an FPGA. Okay, so these are the FPGA. Therefore, we have studied about the first one is we have studied about what is the CLB, computer logic block, that we have started about this one. It consisting of three mode of operations can be operated. The next one we can call it as programmable interconnects. So interconnects that we have started about. Okay, now we are going to see about IO blocks. So the next important component in the FPGA is nothing but IO block. Okay, so IO block, how it look like? So normally this is what an IO block is. Okay, so that means that, for example, whatever the IC that we are considering, for near to that at the edges of the your IC, you can find so many IO blocks here. So many IO blocks, right? All these IO blocks are connected. So that means whenever you want to send some information to this in FPGA, it has to flow through the IO pad. Whenever we want to take the output from the FPGA, so you have to pass it through the IO pad. Okay, therefore IO pads are very important. So without using the IO pad, we are not able to send an information inside of your FPGA or take the information from outside of the FPGA, because otherwise the IC will be damaged without using these IO pads. Okay, now we can see what are the possible output, different outputs can be taken into consideration. As I mentioned that, for example, in point of view, okay, the input is only one type of input only we can view. Okay, there is no possibility of different options for the input. Okay, so the input will be is only one way, but output can be taken, or output can be seen in different forms. Different options can be possible. Okay, one possibility is that we can take the output is inverted output, we can take it. That means whatever the output we have got, if you want to take an inverted output, then we can use the, that means the IO block has a provision to provide the inverted output, right? So for example, if you want to see the tri-stated output, then we can see the tri-stated. So here is the output actually we are getting through the IO pad. Okay, so that means this output can be a tri-stated output. This output can be a latched output through the flip-flops we want to take it, or this output can be a slew rated output. Okay, and it can be a passive pull-up network output also. Okay, therefore the output can be taken in the different forms, either the complemented form, or tri-stated form, or latched output form, or slew rate form, or passive pull-up form, right? For example, what should I consider in order to get the inverted output, for example? So for what I have to do, for each and every output option, we have a configurable memory block. So this is a configurable memory. So that means we have to program this particular memory shell so that it will be act accordingly. For example, this memory shell is equal to logic 1. So for example, logic 0. Okay, then what will happen here is that, so whatever the output signal is there that is generated within this FPGA, okay, so that means in an FPGA, here is we have an output, original output. This output must go to this pad by using this IO block. What is this block is saying that, what is this saying that? So this output can go to the output side, provided that it has to be enabled. Okay, so with this enable input only, it will go. Okay, so whenever we want to inverted output, this all other states, all other possibilities must be disabled. Clear? So therefore, what I have to do, whatever the original output is there, if the original output wants to go in this particular direction to the output side. So when this input is going to the output side in the complemented fashion, what could be the output for, what could be the input for this one? What could be the input for this one? For example, if you consider exclusive OR gate, XOR gate 0 0 0 1 1 0 1 1 output. What is the output? 0 1 1 0. If any one of the input of the XOR gate is equal to 0, it will simply directly sending the next input. For example, if it is 1, 0 0 0 1 1 0 1 1. If this is the 1, this is the 1, this is the 1, what is the output? 0 1 1 0. So that means it's a complement to the next input, complement to the next input, complement to the next input. That means this must make this logic 1, right? This particular one make this is the logic 1. So that means we have to program this memory, configurable memory block, to assign by logic 1. Okay, here is logic 1 we have to assign here, so that whatever the output that we have here, that will be complemented at the output side. Clear? So like this, if we want to have a tri-stated buffer, so we have to disable these particular components. Okay, but we have to allow the only this tri-state, this enable input. So because of this enable input, whatever the output that we are getting, that will be tri-stated. So through this one. Okay, so therefore the tri-state output will get it there. So therefore, for example, when the gate is equal to on, for example, the information is there. If the gate is not on, then the tri-stated output, that means that will be equal to high impedance state can be possible. Okay, so another option is that latched output also. So the latched output is nothing but so the output will go through the multiplexer. The output will go through the multiplexer. So for simplicity, I am removing all these things. Okay, for the sake of this one particular case they have shown, but we can say that for a latched output means we have to set this one to logic. For example, this is 0, logic 1. If you place m is equal to logic 1, then whatever the output is there, that output will go in this way. Okay, so in this direction, what could be the input for this one? It could be logic 0. So what is the input for this one then? What is the input? It must be logic 1. This must be logic 0. What is the input for this one? So I need to have a logic 1 here. If it is a logic 1 here, means what is happening here? What is the tri-state input it should be? Okay, what is the output input? What should be this one? So therefore, for example, if it is a logic 1 here, it should be logic 1. Okay, sorry, if it is a logic 1, it should be logic 0. Then this will be complemented over here. So therefore, this value becomes 1. Something like this, we have to program this memory cells in order to allow the required output. That's what you should remember, right? So the next important one is slew rate. Okay, the next important one is slew rate. How do we define a slew rate? What do you mean by a slew rate? Slew rate is nothing but whenever we want to connect the output to the external devices. For example, this output is connected to the external device, but the rate at which the output is generated in the FPGA is a very fast input signal. Okay, so therefore it cannot activate the other input signals, or it may be, if that the fastness of the change of the output signal is very high, then it's very difficult to monitor that output, and they cannot that are not useful to the external world. Therefore we have to change the rate at which the output is generated, that is defined by using the slew rate. Okay, so therefore by using the slew rate, we are able to control the changes of the output variable when it is connected to the external device, right? So that's what we can understand about the slew rate. Therefore we have to program the slew rate bit value in some other way. Sometimes, so so therefore this slew rate, because of the slew rate, it is possible to reduce the noise introduced when we are connecting the output of the FPGA to the external device. Excuse me. Clear? So therefore the slew rate is possible to reduce the noise when the change of the output may lead to, the fast change of the output may lead to the noise introduced in the external devices, right? So the next one is passive pull-up network. So for example, whenever the input is floating type of input is there, for example, input is not a stable input, if we are getting, for example, then what we have to do? So we have to use the pull-up resistor. Through the pull-up resistor, that floating input variations are easily eliminated or reduced. Okay, the floating inputs are necessarily controlled or monitored by using the passive pull-up methodology. So therefore, by using the passive pull-up methodology, we have to introduce the passive pull-up network, which is a passive resistor. The pull-up resistor we have to use, so that we can control the floating input that is available within this particular FPGA to the external devices. Right. So this is what the IO block that is actually available in this one. Okay. So this is actually the entire information will be there in a particular FPGA. Okay, before going to that FPGA design flow, how do we control the FPGA, or how do we use an FPGA for your design? These are the processes are there. Before going to the processor, let us recapitulate what we have done so far. Okay, so this is the first step that I am talking about here. For example, I'm interested to talk about this one. So these are the this is the entire FPGA chip. Okay, FPGA chip IC, or I can call it as. So we have different CLBs are there, as you can see here now, and at each and every point, you can at every line, in all the directions, we find the IO blocks. Okay, so how the IO blocks will work, that's what we have seen so far. Okay, and the next one is we can see the programmable interconnects, how the interconnects are there in this one. Okay, so what are the different possible ways that you can communicate with the different CLBs that we can see from the using the interconnections. Okay, as I mentioned that all these components are programmable. What do you mean by programmable? Which means that we can set a particular component, we can access, or we can control particular CLB according to the bit information that we are giving. Okay, therefore the stream of bits that are necessary, that should be generated, and we have to give the bit stream information to the FPGA. Therefore FPGA will configure to that particular bit streams, and it can allow the use of the components that is available in FPGA, right? So that's what we can see. Please remember these points very clearly. Okay, fine. Next, another, before going to the implementation, the design flow of the FPGA, I want to discuss about one important concept that is called one hot state assignment. That is called one hot state assignment. Okay, so this is actually normally applicable in FPGA implementation. Whoever do the implementation in FPGA, most of the cases people will use the state assignment technique by using the one hot assignment. Okay, there are the different state assignment techniques are there. What does it mean? So let us look at here. For example, we have a state diagram here. For example, S0 is there, S1 is there, S2 is there, S3 is there. Okay, something like this. So how many states are there? So for some, depending upon the input signal, we can generate how the state diagram, something like this. Okay, for example, if you are considering the the design consisting of these many number of states, how many number of flip-flops are required? That's a question. How many number of flip-flops are required? As we have seen that 4 states are there, two flip-flops are more than sufficient, right? So the 2 flip-flops are sufficient. Okay, so therefore so this is what we can understand about simple state assignment. For example, for the state assignment, 2 states I'm using, right? 2 flip-flops I'm using. 0 0 is the state assignment. 0 1 1 0 1 1 is the state assignment that we have done. Okay, according to the state diagram, we can implement our circuit based on generating the present state, next state, and input, and the truth table, or we can say state table that we can write, state table. Okay, so from the state table, we can generate the equation for the output as well as the next state. Okay, we can generate then equations. So from that equations, we can develop the hardware, and this hardware will be our desired functionality. Okay, so the question is that one hot assignment, in the concept of one hot assignment, so we don't bother about the number of flip-flops. Okay, we don't bother about the number of flip-flops. As a designer, people will think about that, how many number of state I should reduce so that I can reduce the number of flip-flops, right? For example, this circuit, if S3 is redundant, then I can reduce the state S3, so that I can, or maybe S2 is also redundant, for example, then I'm using only 2 states, only one flip-flop can be reduced, 2 flip-flops reduced to one flip-flop. So the people are trying to reduce the number of flip-flops, or the number of reduce the number of states, so that number of flip-flops will be reduces. That is what the main focus in the encoded state assignment technique. Okay, but the people have different orientation now. So because we have a lot of resources are there, FPGA consisting of a huge number of resources. Okay, so therefore we don't bother about the number of flip-flops. Instead, we focus mainly on how do we reduce the number of combinational logic blocks, CLBs. How many CLBs that we can reduce? That is the point of discussion. Okay, therefore it is very important to note that. So instead of reducing the number of flip-flops, okay, we focus mainly on the total number of cells. Reduction in the total number of cells is very, very important. And thereby we can reduce a number of interconnects also between the cells. Is it clear? So the point in the FPGA implementations are we don't bother about the number of flip-flops that actually reduced, but we are focusing on reducing the number of logic cells. Okay, so that the fastness of the circuit will increases. Okay, this is achieved by the one hot state assignment. This is achieved by one hot state assignment. Okay, so therefore, obviously, one hot state assignment actually requires more number of flip-flops. How can you say that? Because for how many number of states are there? For example, in this particular example, I have taken the uh, four states I have used. So for each and every flip-flop, only one. For each and every state, I'm using one flip-flop. How many number of states are there? Those many number of flip-flops I need to use. For example, 5 states are there. 5 flip-flops I need to use. 5 states are there, 5 flip-flops I need to use. For example, 100 states are there, for example. So don't be like that, but 100 states are there. 100 flip-flops I need to use. Okay, so therefore, but in case of, for example, in this particular case, for example, in this particular case, how many number of flip-flops are required? For example, as I mentioned that, for example, 4 flip-flops, 4 states are there. How many number of flip-flops are required? In one hot assignment, four flip-flops are required. In case of normal notation, if we have a 4 states are there, 2 flip-flops are sufficient. Okay, so therefore, but the number of flip-flops are increases if you are using the one hot assignment. So doesn't it won't affect your logic implementation. Okay, how it can reduce the logical implementation in a better fashion when compared to the normal encoded assignment. This assignment, conventional assignment, we can call it as encoded assignment. Okay, so how it will be reduced? So let us see now. Okay, so but we have to keep in our mind that whenever you use the one hot assignment, if you're using the n states, so you can find n flip-flops, you need to have n flip-flops, right? Let us see how it can be possible. For example, let us consider this is the state assign. This is the state diagram. For example, T naught is a one state, T1, T2, and T3 are the 3 states are there. Okay, therefore, how this is how the state diagram is look like that. Okay, so my question is that I want to see what is the next state for the T3. What is the output for T3? Okay, so how these equations will look like? Okay, so that we can understand that how best the one state assignment is when compared to the encoded assignment, right? So for example, if you have in the 4 state, 4 flip-flops are required, there is no doubt. No flip-flop, 4 states are required, 4 flip-flops are required, because we have a 4 states. Clear? Now these 4 states are, for example, this is called Q0, Q1, Q2, Q3. Okay, so therefore at a time only one flip-flop will be active, remaining time all the flip-flop must be inactive. Okay, for example, if you're there in the T0 state, for so I have to mention the flip-flops output is something like this. The first one is 1 0 0 0. So the 4 flip-flops output I'm showing here for this particular state. You can observe very carefully here, only one flip-flop will be active, other flip-flops are inactive. Similarly, for the T1 state, so what is the state assignment here I'm doing? This is 0, this is 1, this is 0, this is 0. This is the state assignment. So therefore here I am talking about in the conventional methodology, this is 0 0 0 1 1 0 1 1. I would have written like this. But now I'm not doing like this. What I'm doing here is that instead I'm writing this is 1 0 0 0. This is the state assignment. This is the state assignment for this one. This is the state assignment for this one. This is the state assignment for this one. Right. This is how I am doing. Clear? Okay. Now, according to this one, for example, I want to talk about the next state equation for the state T3. Okay. Next state equation I want to develop here. How do I do this one? For example, next state of the T3 is nothing but the flip-flop output of the Q3. Okay, so therefore for this one what I have to do, the next state is depending upon the availability of the input is coming here, another input is coming here, another input is coming here, another input is coming here. These are the four are involved in this one for the state T3 in order to find the next state equation. Okay, so therefore the input x1, so the input x1 is multiplied with the state of this q naught, the state of this q naught, and the state of the q1, q2, q3 are is complemented form. So that's what we can write. So what I'm writing here in this particular equation, x1 is the input and the state q naught is required, but I don't want to require for the q naught, sorry, q1 bar, q2 bar, q3 bar. That is what we can write it. Q naught, q1, q3 are nothing but q1, q2, q3 are nothing but all zeros. Therefore the complemented fashion that I have written here. Okay, similarly for the not only that one, this is also is involved here, so that equation also here, so this is also required here, this is also there in this one, so and this is also there in this one. So since these are not required, that means these are redundant terms for each and every term existed in the this equation. These are all redundant actually, so that we can remove all these things. Only availability is that whatever it is required, that is only we can keep it. Okay, that's the reason why we can say that q3 plus the next state equation for the flip-flop 3 is nothing but x1 into q naught. This particular state variable I need to consider. Okay, so therefore only for this particular term q1 is relevant. For this particular term q3, so you can see here in this particular one sorry, so in this particular q3 term, for example the term q3, let us consider q3. So let us consider q3 here, for example. Okay, in this q3 what you can observe, q2 is important for you. Okay, and q2 and q3 and sorry, x3 and q2 is important for this particular state. What is important for you, x4 and q3 are important because it is uncomplemented. So therefore in this particular next equation you can consider only one state variable. Okay, so either q0, q1, q2, q3. So therefore, so if you realize this particular equation by using the logic gates or CLBs, it takes less hardware when compared to direct state encoding technique, but that used in the previously. Okay, for example, if you consider this one is 00 and this is 01, sorry, 01 and this is 10, this is 11. If you are using this one, if you find the next state equation, it's a huge equation you'll find there. When compared to the next state equation, according to this particular scenario, so this hardware cost is very less. This is very less hardware is implemented when compared to this one. It requires a very less hardware when compared to the encoded assignment approach. Okay, because each and every term consisting of only one state variable, but there it's depending upon maybe, for example, if you're using this 00 it may be consistent of q1, q0, q1 maybe be there. Okay, x2, q0, q1, q2 is also there, something like this. It will, a huge equation will be there. Okay, but using this particular one state assignment technique, one particular program is completely responsible to find out one particular state variable only, one particular term. That means this is a one particular term, so this is responsible to find out, this is responsible to find out only one particular state variable only. Each and every term is responsible to find by using the one state variable only. That's what we have to identify that one. So because so to implement this equation, less hardware is required. That's how, if you're using the state assignment technique, there is a possibility of less hardware when compared to the state encoding technique. Okay, so similarly, if you consider output equation, for example, Z1, Z2, output equations are there. Okay, for example, see here, so we can see Z1, Z2. Okay, so Z1, Z2 are the conditional outputs that we have. Z1 and Z2 are the conditional output. If you want to find out this one, if you want to find out the Z1, what are the required states are there? So for the Z1, T naught is required. For the Z1, T2 is required, right? So these two are required. So what are the responsible state variables are there for this one? T naught is required and T2 is required. So therefore, associated input with this particular thing will be considered as one product term. So the T2 related output with respect to the input will give you another product term. So therefore, this particular equation also consisting of only one particular state variable. Okay, one flip-flop output only we are considering, one particular product term. So it does not consisting of x1, q0, q1, something like this, and x3, q2, q1, q0, something like this. We are not looking at this in this way, because this product term should have only one particular state variable, maybe a q0, q1, q2, q3, whatever it may be. This particular term also will responsible for either q1, q0, 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 q1, q2, q3 also. But according to this diagram, we have qt is responsible. So therefore, the red the hardware is high at this point, but the less hardware is required for this one. Less hardware. Okay, you please keep remember this one. Okay, so therefore, this is what it is possible by using the one hot state assignment technique. Okay, so this is useful. So therefore, almost whenever the people are using to implement their circuits in an FPGA, most of the cases the people will think about one hot state assignment. If they are able to achieve their goal with the one hot state assignment, they will go for it. Otherwise, they will come to the conventional approach. Okay, but most of the 78 to 75 percentage of the FPGA implementation, they will prefer to go for the one hot state assignment, because the resource is not a matter for us. But thing is that how can we, the flip-flop resource is not a matter for us. Okay, the matter is that how many number of CLBs that we can reduce, so that the power consumption, the speed, and the area of the circuit will improve properly. Okay, so again we can consider about the Shannon expansion theorem. Already we have spent a lot of time on Shannon decomposition theorem. Okay, um, you can observe this one. Uh, okay, in the last class we have seen how do we implement this one. Okay, let us come to this point later, because some two more examples that we have to give on this particular this thing. So before going to that one, let us see how do we implement your circuit in FPGA kit. Okay, so what is the design process? For example, what is the design flow for FPGAs, which is nothing but designing with FPGAs is nothing but what is the flow that we can, what do exactly the meaning of the designing with FPGA, which means that what is the flow that you can implement your circuit in FPGA. That's what important. Okay, so as we have seen that we have started with the idea. Okay, so this idea has got some specifications that will be implemented, that will be done with HDL programming. Okay, so this HDL program, we need to verify the syntax errors and debugs, whatever are available in this particular HDL description that we have to do. That is called simulation. Next, once the simulation is completed, we have to synthesize our code. Synthesis. So what do you mean by a synthesis? Okay, so whatever the HDL code is there, that code will be translated into the FPGA related hardware. FPGA related hardware. Okay, so whatever the contents, see, carefully understand, whatever the FPGA contents are there, how many some CLBs are there, and that means nothing but the lookup tables will be there. So it will convert your hardware, it will convert your HDL program or behavioral program into lookup table based hardware. Is it clear? So whatever the targeted FPGA that you are considering, whatever the FPGA, whether Spartan or Vertex or maybe Altera, whatever the FPGA that you take. So according to that particular FPGA resources, this program will be converted your that program into that particular FPGA related resources. Is it clear? So whatever the text information is there, the text information will be converted into your hardware based on the lookup tables, or maybe I can call it as simple CLBs that we can use it. Instead of saying the CLBs, better we can consider the lookup tables. So therefore, it will connect, it will take the lookup tables and you can implement your textual information in this form. Okay, so which type of lookup tables it can consider, that's depending upon what type of FPGA that you're using. That's important. Okay, so whatever the FPGA that you are taking, according to that FPGA related resources, it can be considered, and that can be convert to your textual information according to that resource related hardware. Okay, so once we have the synthesizing of this thing is there, then what we have to do, we have to map your design, mapping. So mapping your hardware into a real FPGA. Okay, this is an automatic tools that are available. So only the humans are involved here only. So they are, how they have an idea how the specifications are there, that will be writing in the form of HDL code. Only the designer will focus on this one. Remaining all these things are done by the automated tools. Okay, for the simulation automated tool is there, and synthesis automated tool is there, and mapping also will do the automated tool is there. Okay, what is this mapping will do actually? Mapping, or I can consider partitioning. Partition. So whatever the huge logic is there, that huge logic will be converted into different pieces. Okay, different pieces it will be converted. So one particular piece will be implemented in one particular CLB. One particular piece will be implemented in another CLB. So like this, depending upon the size of this particular piece, whether one CLB is used or two CLBs are used, that will be depending upon that one. Okay, so therefore this task is done by the mapping or partitioning tool. Okay, once this is mapping is completed, then we have to go for placing and routing. Okay, so placing and routing. So therefore, so these FPGAs are, therefore FPGA has got different CLBs, so different connections are there, right? Okay, so one particular the part is implemented in this particular CLB. Another part is implemented in this particular CLB. Another particular part is implemented in this CLB. Okay, that means it is placing the your piece of logic into that particular FPGA components. Is it clear? So that is called placing and routing. Then once the placing and routing is completed, so the bit stream file is generated. Bit stream. So that is called bit stream file has to be generated. So this is actually is relevant information for an FPGA. So this is an FPGA. So this bit stream is dumped into this FPGA. So therefore that means the which components need to be active, which components need not to be active, which components are need to be accessed by that particular information, that information will be available in this bit stream. Okay, so therefore the bit stream will take this bit stream will guide this FPGA. Okay, so that means the bit stream is actually the programming information to an FPGA, so that this FPGA will act according to your idea. Okay, so therefore this is what the flow that is involved in the FPGA implementation. Okay, so all these things we will see in the lab in the next semester. Okay, so far we have already studied about the HDL programming, what how do we describe the circuits, and the simulation also. I have shown you how to simulate it, what is the synthesis, and mapping, replacing and routing and bit stream generation. If time permits, at the last I will show you how to do this thing. Okay, so therefore this is also involved in this form, but exclusively when in the next lab, in the next semester lab, you will directly implement all these things in an FPGA. Okay, so therefore this is the real hardware. You please remember that FPGA is a real hardware. So if you want to dump some information bit stream, so all these are automated tools that we need to use. Okay, bit stream generation, placing and routing, mapping, synthesizing, simulation, these are all automatic tools are required to generate the bit stream file. So the bitstream file is actually programming information. Please remember that there is a programming information. That programming information will provide the necessary connections among the CLBs, and it can generate the FPGA. That we can use an FPGA in our design purpose. Clear? Okay, so let me check what is the time, how much time is there, and then yeah, the time is up. Then please go through the state one Shannon expansion theorem, the basic idea, and how do we implement in this the logic functions by using the Shannon expansion theorem that I have shown you in the previous classes. Please go through it once. Okay. So with this, we have completed the today's class, and only the 3 topics are there.